Welcome back to our lesson on disconnecting means. In this part, we are going to discuss equipment disconnects. 690.15c has the requirements for equipment disconnecting means. These are going to be very similar, if not the same, as the requirements for the PV system disconnect, in that they need to be rated for the maximum circuit current. Obviously, the disconnecting means has to have a current rating more than your circuit current, otherwise you could damage the disconnecting means. It has to be rated for the available fault current. That's the maximum current that will come from the power source that it is connected to, be it the PV array, which would have a small available fault current, or the utility, which would have a relatively high available fault current. And it needs to be rated for the voltage of the circuit that it is installed in. If we have a 1500 volt DC circuit, we need to have an equipment disconnecting means that is rated higher than 1500 volts. Same thing on the AC side. If it's a 12240 or a 408277, has to have a voltage rating to match the voltage of that circuit. The types of disconnecting means are listed in 690.13e, and this is things such as manually operable switches or circuit breakers, connectors that meet the requirements of 690.33d1 or d3, a pull-out switch with the appropriate interrupting rating, a remote controlled switch or circuit breaker which can be operated automatically when the control power is interrupted, or the other category, a device that is listed for the intended application. We need to install that line load warning when it is necessary. That's the warning we discussed earlier that says electrical shock hazard, terminals on the line and load side may be energized in the open position. And keep in mind, as we mentioned earlier, that this is only applicable to places where the line and load terminals actually may be energized when the disconnect is open. Usually would not apply on the AC side, because as soon as you disconnect the utility, the inverter shuts off and there is no energized power source from the inverter side. So wouldn't typically apply to the AC side, would almost definitely apply to the DC side, because anytime you shut off that DC switch, the line side would be energized from the PV array and the load side may be energized from the capacitors in the inverter. Keep that in mind when you are applying labels to these disconnecting means. If the disconnect is remote from the equipment, so that's more than 10 feet or out of the line of sight of the equipment, it has to be lockable. So that way, if we shut that disconnect off, say a combiner box on the DC side of the system that is remote from the inverter, when we shut that disconnect off at the combiner box, we want to be able to lock and tag that disconnect out so that it's not accidentally energized, which would energize the inverter if we're working on the inverter. Here's an example of the equipment disconnecting means. We have both DC and AC disconnects in this scenario. The two inverters each have DC disconnects integrated into the inverter. That's these rotary switches that we see here, one on the right side, one on the left side. That's going to disconnect the DC coming from the array from the inverter, which is the top section here. That can actually be removed separately from the bottom with the disconnect in it, so you could replace the inverter without removing that bottom section. The AC side disconnect is a breaker that is contained within this enclosure here. There'd be a 2-pole breaker for each one of these inverters, so two 2-pole breakers inside that enclosure. If you needed to service these inverters, you'd shut off the DC disconnects, shut off the AC disconnects, lock and tag them each out, and then you could remove the inverter off that enclosure if it needed to be replaced. Now there is an informational note in 690.15c that says it's common practice to terminate the power source conductors on the line side of the disconnect switch, which is the top of the disconnect. So here we see this is a three-phase disconnect. This would be on the AC side of the system. We want to have whatever the power source is that may potentially be energized when we shut the disconnect off on the top. That's common electrical practice. Whatever the energized source is going to be on the top of that disconnect. On the AC side, when we shut that disconnect off, we know the inverter is going to turn off automatically. So the inverter side will go on the load terminals, and the grid connection will go on the line terminals at the top, because that grid connection will remain energized when we shut that disconnect off. Now on the DC side, it remains the same. When we shut that DC disconnect off, there is no energy coming from the inverter once the capacitors dissipate, but there's always going to be energy or potential from the array side. So we want to put the array on the top, the line terminals of that disconnect. So when that disconnect is opened, we know that the potential power source is on the top of that disconnect. Simple thing to remember this is always put the inverter on the bottom side of the disconnect. The DC side, the inverter goes to the bottom. The AC side, the inverter goes to the bottom. That's always the simple way to remember it. Now, with a single throw knife switch like we see in the picture here, we want the blades of that knife switch to be de-energized when it's open. So you can see the little blades here, there's 1, 2, 3 blades. They protrude from the disconnect when that disconnect is open or off. So we want to make sure that those are de-energized when we open that disconnect. Those switches are designed so that when you open that disconnect, the knife blades are attached to the bottom load terminals of that disconnect. That's why we want the power source on the top line terminals of that disconnect, because you've got metal pieces sticking out of that disconnect that are very easy to touch accidentally. So we want to make sure that they're de-energized so that it reduces the hazard when working in this disconnect. Now here are some common disconnecting means. You have equipment disconnects here. This is a regular knife blade switch with the throw lever, a visible lever we can see there. This is a good example here at the bottom of how it is lockable in the off position. There's a hole in the lever itself and a hole in this flange on the disconnect, so you could put a lock right through those two holes and lock this switch off. That's a perfect example of this. It also has this little tab that comes out of the front, so we could lock the cover so that someone can't open that cover and get to the energized parts on the inside. Another option for equipment disconnects are isolating devices. We talked about these in the last section. Equipment disconnects do not necessarily have to be load break rated, so we could use touch-safe fuse holders or module quick connectors as equipment disconnecting means. Isolating devices, those work perfectly fine for that application. The thing we have to remember always with isolating devices is they are not load break rated, so we have to shut the circuit off using a load break rated device and then test for current flowing through that circuit before we open the isolating device to prevent damage to the device and hazard potential to the person working with that isolating device. Now, some quick connectors could be either an equipment disconnect, an isolating device, or both. This is an example of an AC trunk cable from a microinverter. This connecting device here has been specifically listed by the manufacturer as a load break rated disconnect. The current in this connector is pretty low. The output current of a microinverter is around 1 amp. So this manufacturer had this connector listed specifically for the application to be able to interrupt current. You will often see on the DC side of microinverters that the module quick connectors have also been rated for use with this specific piece of equipment as load break rated disconnects. You have to check the manufacturer's literature and make sure that is in fact the case. So even though the quick connectors, typically an MC4 quick connector on a microinverter may say do not disconnect under load, they have actually been listed by the manufacturer for load break rating because the current in that circuit of one module is so low that that connector is capable of breaking that load. Again, have to read the manufacturer's instructions and know what you're working with, how that device is listed, and how you can use it properly to use it as either an isolating device or a load break rated disconnect. Either way, it can function as an equipment disconnect. That's the end of this part on equipment disconnects. In the next part, we will talk about accessibility and we will give you an example of disconnecting means. So join me for that part when you're ready. Thank you.